Mathieu is researcher at the Wuppertal Institute. Okay, you can go on.
Okay, thank you, Simone. So the first author of the paper is my colleague from Wuppertal Institute, Clemens Schneider, and I will be presenting today. So the long title of the paper is Simulating Geographically Distributed Production Networks of a Climate-Neutral European Petrochemical Industry. I diving right in. So please can somebody tell me if you see the second slide, because we experienced a huge delay last time. I was seeing my second slide way after.
We cannot see the second slide.
No, okay. So
yes, right now, yes.
Yeah, you can see it. Okay, I still see my first slide, but okay, I know how it looks like, so I can talk. So in this paper, we wanted to analyze possible futures for European chemical industry on the way to climate neutrality. And in doing so, we wanted to answer a few questions, such as which technology do we need to reach such a target in 2050? When do we need to invest in new technologies, and where should it happen? Which energy sources are needed for that? How much of it? When and where also? And how future production networks, production clusters will look like. The paper goes through the 3 steps of the method that is very briefly mentioned here on the slide. So it presents the scenario narratives, presents the quantification of the scenarios via modeling, and then analyzes the results. In this presentation, given the short time, I'm focusing on the modeling, the second part. So you should see my third slide now. Do you?
Yes.
Yeah, okay. So this is our modeling framework. In the big box in the middle is our model, consisting of 3 modules. This model is fed from the left by our scenario assumptions. So we develop scenario narratives with some assumptions in the paper. They are based on the IPCC SSP2 scenarios. And we also input data from our industry database that has at a quite highly detailed, geographical detail level information on the plants in Europe, what technology they use, how old they are, their capacity, and so on. So this goes into the model. The first module is a stock dynamics model that, based on the assumption for the scenarios, generates the future demand for plastics and the future plastic waste generation. This, in turn, is an input for the second module, which is the invest module. It's a linear optimization model that, based on future demand for plastics and the technology parameters, decides when and where to invest or retrofit technologies to meet the demand while minimizing costs, given constraints on CO2 emissions, for example. I will focus in the rest of the presentation on this module. And then the last module is fed with the output of the previous one. And it's a dispatch module that calculates in detail for each site the actual energy use, the steam use, etc., and the emissions. So I'm focusing on the invest module. The next slide, I guess you will see it before I can see it. It shows how some of the routes, the chemical production routes, are represented in the model. You still not see the slide, I guess.
We can see the HVC production route.
Okay, you can see it. Okay, great, thank you. So in green on this slide, the name of the technologies and the products are the existing technologies that are already installed in Europe and that we have in the database. So from the left, the refineries produce feedstock, naphtha, that is then used in steam crackers to produce the platform chemicals, the olefins and aromatics, or you import from terminals at coastal sites, naphtha, ethane, propane, and you can use them in steam crackers or in propane dehydrogenation, for instance. So this is these kind of routes are implemented in the model, and the red ones, the red products and red technologies, are future technologies that the model might decide to implement to reach carbon neutrality. So instead of importing naphtha, we might import green naphtha, so climate neutral naphtha from overseas, and then use it in steam crackers. We might use plastic waste, put it through pyrolysis, and generate naphtha, ethane, and gas oil that can also be used in steam crackers. Or we might go a totally different route with another new feedstock, methanol, from plastic waste, for instance, with gasification, and then from the syngas, you produce methanol. Same thing with biomass, and then you need, from this methanol, you need a new route, the MTO, the methanol to olefins, or methanol to aromatics. And all of those platform chemicals then go into the polymerization to produce the polymers. So as I said, it's a geographically detailed model. So I'm talking a bit before you can see the slide. So the next slide shows two maps that give you an idea of how, yeah, now you can see it. So on the left-hand side, you have the map for 2020 in one of our scenarios. It's a scenario where demand for plastics goes up until 2050, and the system reaches carbon neutrality in 2050. So on the left-hand side, the green dots are sites for refineries and steam crackers, and the yellow triangles are where you can import products from overseas at harbors. And moving to 2050 on the right, you can see that some of the green dots, especially inland, are gone. So they are no longer in this production system. Some are replaced by the new production routes, methanol, the red dots, sorry. And in some cases, you have both, a combination of both, especially in the big cluster that still remains around Antwerp, Rotterdam, and northwestern Germany, the Rhine region, also south of France, Marseille. So going to the next slide. So we talked about now the feedstock and the platform chemicals. This is going into polymerization. The next slide is a very simple polymerization route from ethylene, one of the olefins, producing 3 types of polyethylene. That's a simple one, also implemented in the model. We have something like, we have 15 different polymers in the model, something like 57 different products, and you will see why in the next slide when it comes up. It's another polymerization route for another polymer called ABS. So I can't see the slide yet. I don't know if you can see it, but you will see that the route is much more complicated than for polyethylene. You have a lot more intermediary steps. You need more products, intermediary products, until you get your polymer. And as you saw on the maps before, those different plants are not necessarily at the same place. Along this chain, you might have to transport the products from one place to the other. So that's the next feature of this model. So moving on to the next slide, it should show 4 small maps that are close-up looks, so kind of zoomed in on the region around Rotterdam and Antwerp, and the Rhine and Ruhr region in Western Germany, so around Cologne and the region where I'm sitting right now. So I can't see the slide, now I can see it. So the 2 maps at the top show you the naphtha pipelines. So in yellow, it's the capacity of the pipelines, and if the pipeline is used, it's gray. So on the left, top left, you have in 2030, naphtha being imported from Rotterdam and flowing to Cologne, and then flowing up to the Ruhr area. In 2050, it looks a bit different. Now you're importing green naphtha, so climate neutral naphtha, from Rotterdam to Cologne also. It's not going up anymore to the Ruhr area. They changed their production processes. But now it's also flowing down towards Ludwigshafen, a bit further south in Germany. It wasn't the case in 2030 because they had their own refinery in the region there. In 2050, the refinery is out. It's not working in a climate neutral scenario. So they import green naphtha. The two maps at the bottom show the same thing with ethylene. In black is the capacity, in white is the use. So actually, usually we don't show these maps to people. They are automatically generated by the model so that we can quickly see what's happening in it, and if something is wrong. And when I built those maps, I could see that something was wrong. Actually, if you look at the two maps at the bottom, there is a gap between Antwerp on the left, and the dots to the right. It's Gelen and then Cologne. There should be a pipe here, so it's a sign that I should go back to the model. Something was not working properly. And you can also see some shipping happening. So between Rotterdam, Antwerp, and Cologne on the Lower Rhine, they are in the 2030. There's a lot of ethane and propane being shipped toward Cologne. In 2050, those products that are not climate neutral are no longer used, and there is, but there is some overproduction of aromatics in Cologne, and then they are shipped the other way for export towards Rotterdam. So I'm moving to my last slide, which is actually bringing us back to the beginning of this presentation. So where we should see again the four questions I had at the beginning. How future technological clusters and production clusters and production networks can look like. So those maps that we can generate from the model help us answer this question. Which energy sources, how much, where and when do we need? That's the job of the next module that is fed from this module that I presented briefly. And the last two questions at a more aggregate level, not only at the site level, but at the more aggregate level, what technology mixes do we see on the way to climate neutrality in 2050, and when is invested in which processes? So briefly, and that's the end of the presentation, the two graphs at the bottom show that kind of aggregated picture. So it's for Germany in the same kind of scenario with consumption for plastics going up. On the left-hand side, we have again those feedstock producing technologies moving from 2020, the red ones moving from refineries, being slowly phased out, replaced partly by waste pyrolysis, generating naphtha, ethane, and gas oil, and then moving further into the future, waste gasification comes in, producing a new kind of feedstock, methanol. And logically, and as a mirror, on the right-hand side, we have the technology using those feedstocks to produce the platform chemicals, moving from essentially naphtha steam crackers today to more and more flexible steam crackers that can use the ethane and the different products from the waste pyrolysis, and moving further into the future, the new route using methanol to produce olefins, the MTO route. So that's the kind of analysis we can do. There's more in the paper, and that's the last. That was the end of the presentation. Thank you for listening.
Thank you very much, Mathieu. I leave the floor to Andrea to look if there's any questions.
Okay, thank you very much for this very interesting presentation. So we already have two questions in the chat, and one is, where is the imported bio-naphtha supposed to come from? Do you have some areas or countries in mind? And to what extent do these assumptions about possible bio-naphtha could falsify the results?
So there are two things. The bio-naphtha, it's actually not bio-naphtha, it's green naphtha, climate neutral naphtha. That's naphtha coming from, so that's the assumption, coming from regions with large amounts of renewable energy, large and cheap, hopefully, that produce then naphtha from hydrogen, from water electrolysis, and carbon that is either captured from the air or from other sources. So that's the green naphtha. There's also green methanol that can be imported that way. So both are quite expensive, but in a climate neutral scenario and in a rising in a scenario where demand for plastic increases, they come into play. We have other scenarios where we assume more circularity and the demand goes down, and those don't come into play. That's for the green naphtha. And then the biomass part, it's for in the model we only in some scenarios we consider it for gasification and then producing methanol. And as a source for biomass, we only consider black liquor coming from, it's described a bit in more detail in the paper, black liquor coming from the pulp and paper industry. So there's also an assumption that this industry that is using this resource today for their own energy production would be willing, if there is a business case, would be willing to sell it to the chemical industry, and they would have to provide their own energy from other sources. So in some scenario we have it, in some others, because it's still a big assumption that this comes into play, in some others we don't have biomass, and so then there is more, as a consequence, there's more import of those green naphtha and green or climate neutral naphtha and climate neutral methanol. I hope I answered the question.
Yeah. Thank you very much. Yeah, this answered the question. And then the next question has been that you mentioned a very detailed geolocated database for these industrial sites. And so the question was, can you tell us what kind of sources you used to improve or to establish this database? And do you also have estimations in your data set, or is all real life data?
So there are many different sources. There are some very how to say mundane sources that you wouldn't maybe think of first, but in the chemical industry, if you keep an eye on all the press releases that the different chemical companies or the chemical industry associations or some other players like the Harbor of Rotterdam, they put out regularly releases announcing a new plant, saying how much, which capacity it has, which technology it's using. And so over the years, so it's something that started at least 10 years ago at the Institute, collecting this kind of data. We have little by little, step by step, assembled quite detailed for Europe. Germany is the most detailed, but Europe is also very detailed. A database on all kind of chemical processing plants. So that's one thing, and we also have a number of projects with the industry itself, where we can cross-check our estimates. Sometimes it is indeed estimates, because the press releases don't say everything. There's also some reports from the industry or from this Verband, from the industry association. And as I said, in workshops with the industry, in different projects, anytime possible, we try to cross-check our assumptions, and so we are relatively confident that we can work with those data.
Okay, thank you very much. Because we also do something similar at Fraunhofer, and we often have to struggle with the fuel mix on a plant-specific analysis. So, what's your approach there? Because every plant has somehow a little different kind of fuel mix.
You mean so say for a steam cracker, what kind of feedstock it's using? If it's using only naphtha, or if it's a mix, yeah. Yeah. So so since we're building a model, we make some simplification of the real world. So we have in the model we have naphtha steam crackers, different vintages of it, so they have different efficiencies and stuff. So we decide which location has which kind of naphtha steam cracker based on when it was built. Then we have ethane steam crackers, and then we have flexible steam crackers. So those flexible steam crackers are more and more in trend, so to say. They can switch between fuels. They can switch between naphtha and ethane and propane and also gas oil. And they are more and more in trend, especially in the last few years, because some cheap, so to say, ethane and propane became available from the US shale oil industry. And so in our model, we have that kind of flexible and steam crackers, and then we don't fix the amount of, say that they use 20% naphtha and 60% ethane over the year, and the rest is propane. Is the model then is using, so during the optimization, it's using a linear combination of all possible inputs to minimize the costs. So it's our model that decides. We know quite well which steam crackers can deal with different inputs for which particular mix of inputs. Then it's the model that decides that.
Okay, thank you very much. At least I do not have any additional questions in the chat. So I think we can move on.
Okay, thank you. Thank you, Mathieu. Okay, the second presentation will be made by Reza, that actually working at the University of Brescia, a PhD student, and the presentation is entitled Assessing the Geographical Aspects of Regional Industrial Symbiosis for European Regions. You will have 15 minutes for the talk. Reza.
Thank you very much. Good afternoon. My presentation would be about assessing the geographical aspects of regional industrial symbiosis networks. So, as we know, as today we saw, there are different aspects for the great challenge of world for providing sustainable energy. Especially in Europe, these aspects are increasing the share of renewable energy resources in the total energy consumption and increasing the efficiency, the technological considerations, as well as regarding to have the two above mentioned points. Industrial symbiosis may be carrier all these points. By definition, industrial symbiosis is the exchange of residues or wastes between two different firms of dissimilar productive processes. These exchanges can cover material, but also non-material services or skills. Regarding our problems for energy efficiency, industrial symbiosis can be realized through the three following topics: waste heat recovery, waste heat connection between the dissimilar processes, or exchange of material residues as alternative fuels, or utility sharing in order to reduce the total energy. But the question would be then, the question would be then, in which manner this work would be more effective? If it would be in individual collaborations, or if it would be scaled up into networks, let's say. In order to have these networks, we should remember that industrial not only, but also it's about in companies from different know normally each other. So when we speak about scaling up, it seems that it would be more complicated for a network of many different actors. Therefore, we will need some sort of support from outside the network, which is usually referred to in literature as facilitation. The structure of this type of regional collaboration usually is referred to as ISN or industrial symbiosis network in order to be distinguishable from individual collaboration. At regional level, the network may also include not only the manufacturing firms, but also other businesses such as waste treatment businesses or also public facilities. This complicated structure should be somehow measured. We will need indicators not only for measuring the efficiency of a network, but also for designing or future tools. Social network analysis, as I this process only about technological aspects. For technological aspects, there are already developed tools such as input-output analysis, such as material flow analysis, such as analysis for considering the reduction in emissions, the efficiency of network in this way. But the structure of networks, the role of different actors, different influential players in this network is also very hard. Social network analysis is a method based on graph theory, which is a quantitative method for measuring the behavior of a complicated structure, let's say a network. It's very normal to show the network as edges, or let's say as a graph with circles, which are the players of the network, the actors in the network, and the relation which is shown by lines. Here in this slide, and schema networks, industrial symbiosis networks in Europe. One of them in the left is a growing network, and in the right we see a network which is declining due to the fact that one of the main actors left the collaboration in the middle of the process. Networks and in the statistical data which are calculated based on this method. There are different indicators such as betweenness centrality, such as density, such as the average shortest path, which are shown here. Of this network. For example, for density, we can see that network A has less density than the network B, which is due to the fact that there is a very big influential actor in the network B, which is by somehow providing shorter path, shorter relation between the actors. But as we saw in the image on top, there is a risk for the sustainability of the network, which is very dependent to the influential player or central, which are very centralized, let's say. For measuring this industrial symbiosis network from, let's say, an internal point of view, SNA or social network analysis is a very good method, but also we need to evaluate the effect of geo context and the behavior of network and the efficiency of the network. Different aspects should be considered. For example, here on the top, we see an industrial zone from Brescia, where I work. We see the agglomeration of industries in this zone among the agricultural zones and the urban center. And in the bottom, we can see the an input-output network between the outputs in red dots and the inputs in blue. We can see that the real shape of the network is very, very complicated, and there are different types considered, such as infrastructure, such as transportation system, and such as potential actors which are now outside the real network, but maybe they can have share in the future. So this method can work as a supplementary method in order to support the social network analysis. And there are GIS-based tools for considering these characteristics. For this extended abstract, we decided to industrial symbiosis European regions. After a literature review, we came to 47 case studies. The work is still open, but up to our knowledge, there is this number. They are not all of them. They are not exactly networks at regional level, but they are large networks. Some of them even are eco-industrial parks, but scaled up and outside their boundaries. Sorry, I'm trying to go to the next slide. We detected three main network structures in the studied regions. First of all, there is the centralized closed systems. In case of energy, the type of networks are networks with a central provider of energy or a shared utility, which is, of course, very normal in eco-industrial parks. Then we have the scattered pairs of firms. They are individual firms in isolated regions, which are by exchange of some type of waste are connected to each other in order to make a weak regional network. And finally, we have the semi-centralized, or let's say more open system, which is the most expanded system, or let's say an image for the future ideal type of industrial symbiosis network. A summary of the regional characteristics for these three types of networks is also provided. Yes, which shows that how these different types of networks depended to their context. However, we also find out that one of the other important characteristics which can compete with the physical geography is the existence of innovation poles, let's say, or research centers in these regions, which can compete with physical geography, and in some cases this may lead to overcome limitation of natural resources or contextual properties. The data that we used are mostly from open source data. We have detailed data from the context of Italy, and so we open for collaborations, especially from outside Italy, to continue this study. So please feel free to contact me, and I want to share with you my email, and thank you for your consideration.
Thank you very much, Reza, for the insightful presentation. Even if you can imagine, I know the situation here in Brescia, but I think that the same situation holds in several countries, not only in Europe, or all over the world. I give the hand to Andrea to let you know if there are questions.
So thank you very much for this presentation. Currently, there are no questions in the chat. So please, if you have any questions, post them in the chat. Maybe I have a question, but do you think that cultural differences could make a difference in what kind of system for industrial collaboration is chosen in the different countries? Or do you think just it's optimizing itself, and in the end, everybody will choose this maybe semi-interactive collaboration system?
Thank you very much. This is a very important question, because of course we know that the framework, the legislative framework is going to be more or less the similar one, but still there are, as I said, there is this social relationships between the people, and therefore different cultural aspects will play a very important role. Example regarding the centralization, or to going toward some sort of let's say bottom-up approach toward the realization of the system, of the network. Right now we can see these differences, and so of course the geographical discussion should not be limited to physical geography. Of course the cultural geography also will have a very important role in this discussion. So the physical geography is the first step. Let's say, for example, the distance of exchanges between the firms, but then it's needed to be considered also the cultural aspects.
Okay, thank you very much. So we do not have any additional questions yet, so I would suggest we continue.
Okay, thank you very much, Andrea. Then we can go to the presentation that will be handled by Jon, that is business logic for bioeconomic collaboration. Jon, please go on.
Thank you, Simone. Okay, I would first like to start out with thanking both the Swedish Energy Agency for funding this project, and also CIT Industriell Energi in Gothenburg, where our colleagues Elin Svensson and Hanna Tornevall helped us out with the study. And I would also like to thank Johanna Mossberg, who was very important at the early stage of this project. She's currently at RISE. So the background of this project is that Sweden has a very ambitious goal that's shared by many European countries, and the goal is to be a zero net greenhouse gas emitter in 2045. However, since the resource base in different European countries looks quite different, the solution in Sweden is to rely on a bio-based economy that leverages the Swedish so-called green gold, our vast forestry industry, and the bio-based resources that we can harvest in these areas. However, in order to do that, we need to overcome a lot of challenges, and one of the largest challenges to date has been to commercialize sustainable innovation. The reason why this is the case is that it's very costly and time-consuming, as well as challenging for the organizations that are involved in these kinds of processes of redefining how they produce value and to whom they produce value. And when you look through the literature and also look in the industry, you see that collaboration is one path that is used in order to achieve this goal. And in the literature, there are different pathways to study this phenomena, but one of the areas that is explored less than others is the potential to collaborate over so-called value chains, and also collaborate in order to establish new niche markets, which are very important for new sustainable innovations. So the purpose of this project and the paper was to explore the business logics of newly formed collaborations that cut across industry value chains. And they cut across these industry value chains in order to create new markets for bio-based sustainable innovations. When we go through the theories that are used in order to study this, we find that there are many different concepts. And one of the most popular concepts when you look at a firm level is the business model. And a suitable business model is considered to be vital in order to achieve a commercial product. However, business models function within markets that are sandwiched in global value chains, which means that if you start to change a business model, you will make changes that might affect actors all through this value chain, which makes it very difficult to change a business model with regards to the vastness of international industrial value chains. So when you look through the literature and start to ask what is the factors that are being assessed when you consider if a business model is viable or not, you start to encounter different aspects that you need to try to conceptualize into some sort of theoretical concept that can be used as a frame of reference when you start to discuss the business model. And this concept can be conceptualized in different ways, like, for example, a market logic, etc. But we choose to use a concept called business logic. And what we mean with business logic is that it describes the conditions and the necessary parameters that a business model needs to meet in order to be viable or considered viable within an industry. So the business logic is something that describes success factors that builds on an overlap of theory that is a conceptualization of how the world works, about history, which describes what is it that this industry or sector of actors have been going through and what they consider themselves to be. It has to answer about experimentation, which means the kinds of methods that are used in order to try out what it is that works and doesn't, and practice, which is the practical knowledge that the individuals working in the industry relies on. So when collaborating across value chains, the business logic will be a key concept to rely on when trying to understand the context that fosters vital markets and business models. Considering this kind of complex concept and the way that we defined it, it's important to realize that this is not a concept that is easily quantifiable. Instead, it's something that deals with the views of the different actors within an industry, etc. So we're dealing with something that has a high degree of quality in it, and something that's not very easy to quantify. So we started out with a case study approach in order to explore what kind of different cases that we could identify where we both could find examples of cross-industry collaborations, and where we could explore the attitudes of the individuals engaged in these kinds of cross-industry collaborations. And in order to do that, we went through a large amount of different collaborations. We mapped out the entire bio-based industry in the Scandinavian countries in order to find such examples. But unfortunately, it was very difficult to identify successful examples of cross-industry collaborations. So we ended up with only 4 successful case studies. And when we had identified them, we started examining the context in which the initiative existed by going through the business environment, looking at the market settings, etc., looking at the policy instruments that were directed to these markets, and studying specific policy documents and also interviewing experts within each of these sectors. So with that as a background, we started to look into the specific business models employed in each of the cases. And here we used interviews, and we also studied annual reports and homepages, etc., in order to get a feeling for how the business models for each project or case looked. When we did our interviews, we interviewed the founders and CEOs, but also investors. So we had the top people associated with each case study involved in the project. One of the biggest challenges when employing this kind of a method is that it can be very difficult to identify suitable cases, and that was our situation. So it was very rare to find successful collaborations that functioned in this way during the period that we were looking, and that was 2015 to 2018. So the results. We managed to identify, as I said, 4 different cases. One was, the first one was a joint venture that produced a drop-in fuel, which is a fuel that could be used in existing value chains, that was based on wood-based naphtha. And we had an ethanol-based system solution that was directed only towards heavy transport, that was similar in many senses to the first one, but it differed very much in the characteristics of the case. And then we had a wood-based beverage carton that was produced by an international collaboration with which worked both in Finland and Sweden and Norway. And last, we had a symbiotic industrial system that was concentrated geographically, but it had a very mixed bag of different products that emanated from this industrial system. So when we looked at this case setup, we analyzed them, and we, in the paper, we present 5 different analytical angles of interest. I will start from the right to the left. First of all, we were interested in the market scope. Where were these innovations going? Did they really go into the desired route of establishing new markets? Well, 2 of the cases, they went into existing markets and held niche sections in those markets, for example, in the fuel market, while the other 2 cases tried to establish entirely new markets, and in those cases struggled quite a lot due to the problem of trying to fit within regulations and trying to nestle themselves into a system which is highly regulated. Then we looked at the strategy for these bio-based solutions to get into the technical or market structure. And in both 2 of the cases, the first one and the third one, the strategy was to develop something that would be identical to existing projects in order to make the switch as easy as possible, while the other two cases try to create an specific strategy, which was more appropriate to their product, but made it more difficult for them. Then we looked at the technology and the infrastructure necessary to get these innovations in place. And in this area, the study gets quite detailed, but a general conclusion is that there was a reliance on a mix of technologies that really put pressure on the actors that collaborated in order to get these things get them going. And this was also a very big challenge for the actors to get the mix working. It took a lot of trial and error to get the technological parts functioning with the new innovations. And we have the collaborative focus. When you try to cut over industrial value chains, you need to decide how you're going to work with the different products that already exist and the resources that you have. And in these cases, the collaborative focus was quite different in all of the cases. So the partners either choose to combine resources or products or processes. And we had one case, the third one, that chose a completely different way and worked with the third-party certification process instead. And when we apply our business logic concept, we see that all of these cases are unique, which made it difficult to make any general conclusions about how you can, for example, support these kinds of initiatives. So we have a visual representation of these kinds of flows, where the green arrow here is the final stage towards the market. And as you see, the multi-product concept is the most diverse, but also the most complex, and they haven't gotten as far as the secondary product, which is nowadays a multi-billion SEK sector. So it's a very successful area. Conclusions. First of all, when we look at the markets that these products are targeting and how let's say the substitution of different products can be done through these kinds of collaborations, we see that there is a potential for scaling, but it is limited. And that the policies that EU and Sweden has with regard to the scaling of these products is quite fiercely contended, which means that it's very difficult for these actors to decide if they are going to continue with these innovations. And that puts off the investors and makes it difficult for these companies and the collaborations to survive in the long run. This might also be one of the big reasons why it was so difficult to find successful collaborations to study. Basically, with that I mean basically the political risk in this area is so high that actors prefer to find technology that fits with their existing business logic and their existing value chains. And as you saw, the findings indicate that there are 4 initiatives that are very diverse and very different, which means it is very difficult to draw any general conclusions based on these cases. And it might also be that it's can be, however, useful to use them as cases for success stories, and that these can function as models for other let's say, initiatives. However, if you want to go that way and interpret the results in that way, you have to be aware that it's very difficult to transplant the results to another context. It might be the case that there are timing factors in the collaborations and unique resources that are related to these cases that makes it impossible to copy the cases to other contexts. However, we hope that that's not the case, and in some way that we can, at least in the Swedish market or in other areas, can use these kinds of strategies in order to support cross-industry collaborations. So thank you.
Thank you very much, Jon. Maybe we have some minutes for the question from the audience. Andrea?
So also from my side, thank you very much. We do not have any questions yet, but maybe I have a question. So you said unclarity and little political security is one of the big barriers why these collaborations are not successful. So what would be your message to policies? Where would be the main driver to support this? Because this is, at least if you look at the Green Deal, where circularity and collaboration is a big issue, still we are far from supporting our industries to really follow this path. So what would be your recommendation?
My recommendation would be very traditional. I've been working with policy support of industries for 12 years. And if you go through the research, almost all of the research point to one thing, and that's that policy needs to be predictable, and the industries need to have a long time horizon. And in these cases, the time horizons have been very, very short. In some cases, only a year. And we're in the situation right now in Sweden where there are decisions being made right now about the policies that are going to be in place next year, which means that there are only 3 to 4 months of a time horizon, and that's way too short for industry. We have to remember that industries are not monoliths. They're not creatures that we just can poke at and get them to do things. There are individuals and there are groups of individuals that need to communicate and establish agreement on where to put their resources in order for those investments to be done in the most efficient way. So yeah, that's a very long answer for a very short point.
Thank you very much. And I see we have additional question from Mathieu. So he's saying Sweden is having the largest or a very large pulp and paper industry, and the chemical sector is also one who will have to keep working with hydrocarbons. So do you have any ideas or hints how these two sectors can cooperate?
Yes, one of the examples was actually this. So of course the cases are anonymous, but they are trying to work with these technologies, and there are solutions on the market already, as you saw. However, it's very contentious since the market in Sweden is too small for these companies to sell their product only on the Swedish market. So they need the acceptance in other markets like the EU market or in the US for their products. Yeah, we have examples, but they are reliant on long-term plans, just as any other sector.
Okay, thank you very much, Jon. I do not have any additional questions, so if we have time, maybe we have more questions in the end of the session. Thank you.
Okay, thank you, Andrea. Next presentation will be provided by Ricardo Amon. Okay, we have your presentation here. Thanks. Ricardo will provide a practical understanding of the water energy nexus in agriculture production and industrial food processing. And of course, Ricardo leads the California Energy Commission Energy in Agriculture program. Thank you, Ricardo, for joining in early time the conference.
Good morning. Thank you for the invitation to participate with the eceee Industrial Efficiency 2020 conference. We will speak about the methods and the practices that we have used to conduct agro-industrial water energy nexus assessments at food processing facilities. Hello, my name is Ricardo Amon. I have been an independent researcher working in the subject of water and energy in agriculture and the agro-industrial sector for many years. Since I came to UC Davis almost 10 years ago, I have been collaborating with Professor Christopher Simmons in the Department of Food Science and Technology. For this effort that we're going to be presenting to you, we also collaborated with Professor Ned Spang from FST and Scott Peterson, a master's degree student from. The purpose of being here with you today is to transfer information about the methods and the practices that have been developed to conduct water energy nexus assessments at agro-industrial facilities. Our objectives are to be able to establish the operational efficiency of the nexus system in food processing, tomato processing, breweries, creameries, all types of processing facilities where water and energy intersect. We want to be able to estimate the resource use intensity, develop indicators that will tell us what is the water energy intensity of the relationship by unit operation throughout the facility. It allows us to identify water conservation and energy efficiency measures, giving us more granular information to see things that otherwise we may not see, and also allows us to establish a baseline that with it we can then measure and validate results of projects that would have been implemented as a result of the recommendations provided. There are many benefits, and truly there is a direct opportunity for energy efficiency in many cases, particularly on pumps, some steam systems as well. But then it allows us to look at water conservation opportunities that may not have been as clear before. Obviously, when we can conserve water that has embedded energy in it, we're going to have double cost savings. And then we can see if we're doing an impact on thermal energy demand, we can see then a reduction in greenhouse gas emissions. And with any type of water conservation that we can achieve, we will see a reduction in wastewater discharge. We also see that there's improvements in the productivity of the workers, the people that are in charge of the assets. As they gain more operational data, they have more visibility to be able to identify things and get engaged and maybe preempt inefficiencies for the following seasons. The following slides will provide a description of the methods that we use to conduct a materials and energy flow analysis using engineering protocols developed by the American Society of Mechanical Engineers and the U.S. Department of Energy, providing analytical tools to conduct industrial energy system assessments. The water energy assessment model integrates the MEF systems with these protocols in order to establish the operational efficiency of the energy assets that are engaged in beer production, which is our case study for today, where we analyze the steam systems, water pumps, air compressors, refrigeration systems, and fans in order to establish metrics that allow us to determine what is the water energy intensity of the facility and per unit operation. These indicators provides us with a baseline conditions. It allows us to identify water and energy conservation measures. It gives us a foundation to calculate costs and benefits, and then allows us to be able to compare and measure and validate results. The system boundary stays within the production industrial facility, where raw materials, water, and energy come in to generate beer, as a result creating residues, water, and other biomass, as well as air emissions. We established the water and energy relationship. We identify all of the energy assets that are engaged in this relationship. We create a pathway to understand where those water interacts or is affected by power, both thermal and electric, to create steam, to generate steam that is used throughout the facility, and as well as to provide heat for the process, using electricity as the power source to operate pumps, compressors, refrigeration systems, and all of that creating a flow of product with water embedded and with energy embedded within that water, that some of it, most of it, will be packaged as beer at the end of the process. I'll just give you another second to see the image. Thank you very much. We use Sankey diagrams to illustrate the energy balance. The supply side of electricity and natural gas, and the demand side of how these energy resources are utilized, where they are utilized, in what proportions, and what are the final products within that system. Municipal water is delivered to feed the brewing facility with the most essential, if you will, of resources in order to create steam, in order to provide fresh water for multiple purposes that are distributed throughout the brewing facility in such a way that this diagram gives us a visual illustration of how much water is being used, where it is being used, and what is the final outcome of that water that was utilized for beer production. Resource intensity metrics are foundational for us to have a grasp of what is happening in the facility, where we can see the water intensity, the energy intensity, as well as the combined water energy intensity that allows us to measure the amount of energy that is consumed per barrel of water that passes through the brewery, giving us information that gives us an insight into this relationship that is clear, that is consistent, that it can be replicated over time in order to assess where do we have opportunities to reduce the intensity in order to achieve optimization of resource consumption. This table provides very specific results by unit operation. We label them WEN points, water energy nexus points, throughout the facility, where we then can see the amount of water that was passed. We can see the specific energy that is consumed. We can calculate the intensity of this relationship. We can understand where the resources used within the water energy nexus system and outside of the water energy nexus, so that we have a full, complete picture of the facility, and with it create a map that allows us to target specific areas within the facility where we can see opportunities to increase efficiency and reduce waste. The ultimate goal of conducting water energy nexus assessments is obviously to identify resource conservation measures. We know that any reduction in specific consumption will result in cost savings. We are also interested in identifying water conservation opportunities where there is embedded energy, reducing a specific energy consumption, allowing those cost savings to accumulate. Reducing water losses in areas of high energy intensity is also going to reduce the demand for thermal and electric energy, both of which can provide direct and indirect greenhouse gas emission reductions. It also allows the energy utility companies to target water conservation measures with embedded energy as part of their efficiency programs. These high water energy intensity areas can be prioritized, and then we can increase resource efficiency and reduce cost. Yes, there's always going to be high water consumption with less energy intensity that can also be optimized to reduce the volumes of wastewater that have downstream energy implications as well. So we have modeled the brewery. We have analyzed the water energy nexus to establish the amount of energy that is embedded in the water that is packaged in the barrels of beer that are produced. It's as clear as a metric as we need in order to properly compare the resource use efficiency of this facility against other facilities over time. The WEN model gives us high resolution details, offering us tactical options to identify resource conservation opportunities, providing us with operational water energy intensity metrics that give us benchmarks to identify inefficiencies, calculate conservation options, validate results, and compare against peers. We believe that these methods are very practical, they are scale neutral, they can be adopted across the board where there is any kind of industrial water energy relationship. In the food industry, obviously water and energy are essential to produce what needs to be done in order to deliver goods and services. Hopefully this methodology is found to be attractive or useful. It takes time. There is work that needs to be done to produce quality data that is operational so that we know at what level are the systems operating at the time when the assessment is done, such that when we do them again after we have implemented recommendations 2, 3, 4, 5 years later, we can have a very practical metric to compare against. Well, thank you for your time. It's been fun. I would have loved to have gone to Sweden. We had a whole trip planned. We were going to go up north into Norway and then move all the way across to eastern Sweden to go up to the north, maybe then drop to Stockholm and be there again after having been there a couple of years ago in a trip where we had some fun with my son playing jazz during those days. And so, again, thank you. I hope that this is all useful. I'm looking forward to continuing to participate with your conference and to stay engaged with eceee, as I have been with the eceee here in the United States over the years. Thanks again.
Thank you very much, Ricardo. Okay, Andrea, thank you. Should we go through the questions related to the presentation of Amon, or maybe we also can discuss some additional questions from all other presentations?
Yeah, currently we do not have any additional questions in the chat, so I really ask you to participate and give our presenters some additional questions to make it worth their time being here. Maybe I would have a question on the water energy nexus Ricardo presented. So you said, and it looked like this because you had this Sankey diagram. So this is a really data intensive process. I can imagine you did here for the brewery case. So how long did it took you to gather all the data? And is it feasible to do this for other industries as well? Or would this be really a very time consuming process for you?
Thank you. I think the issue of how long does it take to collect the data is relative to the facility. To the extent that some industrial facilities may be better set up in terms of data collection infrastructure. For example, if we had pressure gauges in the inlet and outlet of all the pumps, that will facilitate the data that is needed to calculate the efficiency of the pumping systems. There could be other, so to that extent that varies. It requires understanding and calculating what it is that we're working with. And so at the end of the day, it's almost as if, yes, it's important to be efficient with data collection, but you still need to collect the information in order to have your baseline. And I think that we tend to want to cut corners when it comes to establishing operational baselines, just because it seems like too much work. But at the end of the day, it's like you put work at first and then you reap the benefits. Because when you use mega data, utility meter data only, you really are flying blind. You may be able to see the big picture, but you don't really know what's happening in the ground. So I would think it can be optimized. We were working towards the idea of establishing more sensors throughout the facility, similar to what we do here in California for boilers, where all the boilers right now are working with SCADA systems. And so they have optimized the data collection and analysis automated so that the operators can keep those boilers at peak performance so that they don't emit more NOx than they are allowed to. In the pumps, we don't have that capability yet, infrastructure, mostly because it's not regulated. And so if we were to regulate the performance of pumps, then there would be more interest in that regard. Thanks for the question.
Thank you. Simone, do you have another question?
Yes, Ricardo.
Yes.
Can you give us an examples of other sectors what is interesting and the methodology can reveal different results from other approaches? When it is apart from, as you already said, in the brewery sector, other very interesting sector where, from your experience, it is useful to adopt this methodology.
Yes, thank you. As a method, definitely there's a cross-cutting across the board. We've used this methodology in industrial tomato processing facilities, being able to identify not only direct efficiency opportunities and water conservation also. We've had some visibility to see potential for waste heat recovery that would allow for further water conservation. And so it's similar to what we were saying with Andrea, that once you have this data, you actually can see more than you otherwise would have. And then you start seeing some synergisms in the use of the resources. So to that extent, it's a very useful, and it's also very much of a public domain capacity for engineers to look for the guidance and the standards and the protocols and implement.
And as an additional question, if I understood well the method applied in the brewery, you took the raw material as it is. Is it also possible to include the water and energy expenditure in the agriculture phases?
Of course. And definitely. I think that obviously we would be conducting a separate WEN analysis. Now you have multiple agricultural commodities that are fed into a brewery in terms of different plants. And each of them would have to have a water and energy nexus analysis done. And it's also going to be dependent upon the location where that crop was grown. If the crop is grown in California, we would think that we're going to have a much higher water energy intensity than if the crop is grown in the East Coast or in the Northwest, where there is the water scarcity is not the same.
Okay, thank you.
Thanks. So then we have just one more comment from Mathieu, that he really liked your Sankey diagrams. So as we all know how much work this is, so, and I think I do not see any additional questions in the chat.
Thank you.
Okay, just see a few minutes. Anyway, I can quickly sum up main outcome of this session, on second session of panel 2. Of course, the geographical aspects, more or less, as you capture in different presentation, play a significant role in the decarbonization of industrial processes. Of course, as just underlined, also the different methodology can be used to assess different aspects or different impact coming from different geographical location. Of course, there will be time after the presentation of this section. In the agenda, we will have a short break, and then there will be again some networking activities. So keep track of the agenda in the WUVA link. So there will be a networking session, and of course tomorrow again we will have a couple of sessions. The first session will be mainly devoted to the decarbonization of manufacturing processes, so circularity and decarbonization of manufacturing processes, start at 12 p.m. and then at 2 p.m. there will be an additional session on energy and material efficiency along the value chain. So I warmly invite you to join the two sessions of panel 2. I think we, even if we have experienced this for the first time, at least in this conference, this support, I think that everything went quite well, and I hope to see you later in the networking section, and of course later tomorrow in the additional 2 sessions of panel 2. Andrea, do you want to say some regards? Or?
No, I'm just also looking forward to see you tomorrow in the panel 2 sessions, and thank you very much for all your very interesting presentations.